So Luisa is a research fellow currently at the Max Planck Institute for Astrophysics in Garching, where she's moving very soon to Hamburg as a junior professor, so in 2 weeks. Thanks for coming in this, during this moving period. Before that, before moving to Garching, she was in London, where she did a study as a PhD at the UCL. And she's one of the leading experts in the field of application of machine learning to cosmology and astrophysics, and today she will tell us about explainable deep learning models for cosmological structure formation.
All right, thanks a lot for the introduction, and hi everyone. Yes, so today I'll be telling you a little bit about the work I've been doing in this field of explainable deep learning models for cosmological structure formation. Okay, let me start with a little bit of introduction in cosmology. So our standard model of cosmology, the lambda CDM model, relies basically on 2 very well-established theoretical frameworks, and those are the theory of general relativity and the standard model of particle physics. However, it also relies on 3 other ingredients that do not have such a well-defined theoretical underpinning. Those are, first of all, dark energy, that is a form of energy that we think is responsible for the accelerated expansion of the universe at present time. Then we have dark matter, that is a form of matter that is far more abundant than ordinary matter in the form of stars and gas. And in this lambda CDM paradigm is thought to be cold, meaning that it has very little weak interactions with the standard model of particle physics. And then the third component is inflation, which is this phase of a very accelerated expansion at the very beginning of the universe that sourced all these tiny fluctuations and then gave rise to all the structures that we observe today in the universe. And so really trying to understand what the nature of dark energy, dark matter, and also understanding the origin of a universe in the context of inflationary models is really what motivates us to continue looking for new ways of testing this lambda CDM model. And so the primary testbed for the lambda CDM model has really been the cosmic microwave background. So this is essentially a relic radiation at the time of recombination at very early times that radiated all the way to us. And we observe today in this full sky map of temperature anisotropies. And so these temperature anisotropies in the cosmic microwave background are tiny. So the density contrasts are something like 10 to the minus 5, which means that we can very well describe these kinds of maps, these kinds of fluctuations with linear theory. And this predicts that these kinds of fields are very much Gaussian, and so we can understand them very well and model them very well with linear theory. However, it gives us, a limited picture of what the universe looked like at very early times, and so we only have a limited statistical power in again trying to test our cosmological model. And so if we then forward, about 13 billion years from the time of that the cosmic microwave background was released, we arrive at today's, much more complex and much more nonlinear large-scale structure of the universe. So this time, the density fluctuations are not at order of 10 to the minus 5, but they can reach, density contrast of 10 to the 3 inside dark matter halos, and even 10 to the 30 inside stars. And so this huge now dynamic range that we have in the sort of density fluctuations that we have in the large scale structure at present time means that we can't use any more linear theory, and it's much, much more complex to model this nonlinear large scale structure of the universe. And so, why do we care about modeling these large-scale structure? Why can't we just stick with the CMB that is very easy, linear to model? And the reason is that we think that, these cosmic structures that populate this large-scale structure distribution actually contain information about fundamental physics. So if you zoom in and look at, what forms this large-scale structure, you have cosmic voids where you have most of the empty regions in the universe. You have dark matter halos that populate these sort of nodes of this cosmic web, and filaments that go sort of around the cosmic voids. And the properties of these structures, their distribution, their abundances can tell us something about those fundamental questions I was saying at the beginning. For example, is dark matter cold, or can we actually trace, have some signature what the physics of inflation was, for example, from cosmic voids, and similarly about the nature of dark energy. And so, this sounds sometimes a bit vague, at least to me, when you hear, okay, you can do fundamental physics from large-scale structure. What does this really mean? And I just wanted to give you an example here of how, for example, the distribution of matter, the density structure of dark matter halos contains signatures, for example, on the nature of dark matter. So this is some examples of sort of Milky Way-like dark matter halos in simulations of cold dark matter, which is our standard paradigm, and different dark matter scenarios where basically you assume some form of some effective theory. So if dark matter was not completely cold, but warmer. And so you can see immediately that there are striking differences in the structure of these dark matter halos, in particular the number of substructures of all these tiny halos inside this bigger apparent halos differs, and sort of you end up having more visible caustics as well in the outskirts of these dark matter halos. So, okay, so what is the challenge, right? So how can we actually extract this sort of fundamental physics from the large-scale structure? Well, the challenge, as I was saying earlier, is that this process, the formation and the evolution of these cosmic structures is highly nonlinear. So you have, gravity evolving over time, and it's affected by very complex nonlinear physical process that primarily involve the dark matter. So the dark matter is really what sets the backbones of this large-scale structure, and then the gas and then the stars typically fall, trace this underlying dark matter structure. And so this is a simulation run by the illustrious team showing you the evolution of the dark matter, and you can see how basically things that are more clusters tend to become more and more clusters, so you form bigger and bigger dark matter halos where the gas does also its process, and you see the stars and the star component of the galaxy start forming inside these dark matter halos and in the filaments. And so the issue is really, trying to model how do we understand, for example, the structure of these dark matter halos, how they form, their properties, if this process is so highly nonlinear. And so in our community, machine learning has been advocated as a tool to try to address some of these issues that come with analyzing this nonlinear large-scale structure field. And, probably, 4 or 5 years ago, we'd have to say, oh, what has machine learning really done for cosmology? But I think now, we can agree that it's really brought forward tools that allowed us to do science in cosmology in a way that was not possible before. And these are just, 3 examples where I think machine learning actually has made significant progress. One of them is in the context of generative models. So I was telling you earlier that we have to use these simulations to model this nonlinear gravitational evolution, and they're, very computationally costly. So machine learning turned out to be a very helpful tool to try to sort of substitute very computationally costly forward models with what we call emulators. So basically with machine learning, you can learn how to emulate the output of a very expensive simulation and provide that output for new samples in your input parameter space much, much faster. And so this allows us, to look at the outputs of those costly simulations in seconds rather than many, many hours. Another place where machine learning, has proved very successful is in the context of trying to extract more information from the large-scale structure than what we can do with traditional summary statistics. So traditionally, we do cosmology with things like global summary statistics, like the 2-point correlation function that we know can only be complete if your field is Gaussian. And so deep learning, and in particular, for example, convolution neural networks, are models that allow you to extract a nonlinear complex pattern from the data, and so have been used to try to extract some of that non-Gaussian information that is in, for example, the large-scale structure density field. And finally, one application that I'm particularly excited about that is more for the future, I think, than really about now is the fact that machine learning has enabled sort of a new paradigm in which we do cosmological parameter inference that is called implicit likelihood inference or simulation-based inference. So what this means is that typically in cosmology, we write down a likelihood and we sample that likelihood and do parameter inference that way. Here, basically, with machine learning, you can completely bypass the difficulties and the challenges in writing explicit likelihoods, but just forward model your data and learn that joint probability of the data and your cosmological parameters with a machine learning model. So all you need is a simulation or a forward model that can simulate the thing that you observe in data, and then machine learning does the joint probability distribution for you. And so I think, these three are really, at least in my view, the three applications in which machine learning has really made a difference in cosmology. So what I've been focusing on basically throughout my entire career basically is a new frontier of sort of what goes under the name of explainable AI. So we have these machine learning models that we know can extract very complex nonlinear patterns in data that we can't really write down or model analytically. So can we actually use this model to, not just to give you a fast prediction or to do cosmological parameter inference that we could have done with another technique, but can we actually learn something new about the underlying physics that the machine learning model is modeling, if we can interpret what that deep learning model is using? So can we actually use these machine learning models to extract new knowledge about the underlying physics? And so this sort of requires a different class of machine learning models that go under, this explainable AI umbrella. Okay, so what is the issue with these explainable AI models? And basically, in machine learning, there is this typical trade-off between interpretability and the predictive power of the model. So you can say, okay, I really want to, understand everything that's going on, be super interpretable, and then you can go to a linear regression model or a simple binary decision tree, but then you're limited either by just a model that can learn only linear relationship or just a simple, binary split of your data. On the other hand, you can go to, state-of-the-art, the most complex machine learning models that really they're much more predictive because they can do sort of feature extraction directly from the raw data. So you can give it the raw data and these models learn to extract the relevant features that are then used for the final predictions. Whereas these more like traditional machine learning models require some sort of featureization of the data. So they require a human step where you say, I extract some informative features that then I use as input to the machine learning model. And so this is really what makes it hard to, use the most predictive models, because they come at the cost of millions of parameters, making it really hard to understand what features are they actually extracting from the data and how do they then combine them to make a final prediction. And so, at least in my view, there are, two requirements for developing these explainable AI models. And one of them is interpretability that I already touched upon in the previous slide. And this really means like accounting for why a machine learning model reaches a certain prediction. So this can mean, for example, you go into a layer of your neural network and you see, okay, layer 1 is learning some edges this way, layer 2 is learning some edges in this other way, and then they combine them in some weird pattern in subsequent layers. But then that's not really enough, right? Because if then you can't relate that patterns that you see in the layers to the relevant science domain, you haven't really learned anything about the physics. So you don't just need the interpretability part, you also need a step of explainability, which is basically that maps this account onto existing knowledge in the relevant science domain. And I want to make the argument that actually I think a lot of physical models, even in cosmology, are not really explainable. And what I mean by this is that, you know, we can measure a lot of properties of the logical structure from simulations. So we can run a simulation and then we see, okay, there are these emergent properties of the logical structure that tend to have some sort of universality properties, for example. So what this means, for example, again, in the context of these halo density profiles that are measuring basically the spherically average density of a dark matter halo as a function of scale, we see that, you know, you can take dark matter halos that differ of 20 orders of magnitude in mass, and all these halos tend to have a similar shape in the dark matter profiles. And so we can measure this, we can see it in simulations, yet we can't really explain where it originates from, like where this universal emergent properties come from. And similar with the halo mass function, this is another very important probe that we can use actually to make cosmological parameter inference, which tells us that, okay, if we, this is basically the abundance of halos as a function of mass, so how many halos you have at different mass scales. And, you know, if we plot this quantity in terms of some, in terms of this sigma, which is basically the mass variance, we can plot basically all the different halo mass function onto the same curve. So we can take whatever cosmology you want, but then I can put it on the same shape in this universal halo mass function. But then when we go look in simulations, we actually see that there is non-universality. So there are deviations from this universal theoretical predictions that, again, we don't understand where this comes from. And so, you know, these are exactly the quantities that are then needed to do our cosmology. And so I'm just saying that explainability is not just a problem for machine learning, but it can be also in the context of cosmology, at least on nonlinear scales. Okay, so let me tell you a little bit about the work we did in the context of halo density profiles with machine learning. So we started off, this was work I did with Susmita Adhikari and Risa Wexler, where we started thinking about more in terms of the theoretical foundations of these kinds of cosmic structures. So we wanted, you know, again, we know from simulations that, you know, massive dark matter halos are the result of this complicated nonlinear evolution throughout cosmic time. We see this happening in the simulation, and you see basically the final structure of it is a combination of, you know, smooth accretion of matter onto the dark matter halo, but also some violent mergers with other cosmic structures that tend to fall into the larger dark matter halo. And so we wanted to understand, okay, so out of all this complex, you know, evolution history of the halo, can we find some regularity? Like what determines the final structure of clusters? And so we were interested, again, in the interpretability side, doing this with machine learning, but maintaining interpretability. And so we picked a model that, you know, is still on the interpretable side, but it's pretty predictive. And these are gradient boosted trees. And the reason why they're interpretable is that you can actually measure feature importances. So what this means is that features is just a machine learning jargon to mean the input to your machine learning model. And you can actually measure how important these different features that you've used as input are in determining your final output of the machine learning model. And so this is what we did. We used as input the mass accretion history of the halo, so the mass that the halo accreted as a function of time. We provided it as an input to the gradient boosted trees, and then we asked the gradient boosted tree to predict the final, in this case, the mass profile of the cluster at redshift 0. And so what I'm showing here in this left panel is basically the importances of the mass as a function of scale factor or redshift or time in determining the inner part of the cluster, so the inner structure all the way to the outskirts. So this basically tells you how important is the mass accreted at a given time in determining the final mass profile of the cluster. And so if you zoom in into one of these columns, we basically found there are three most relevant timescales to predict the profile of these clusters. One of them is basically the formation time of these clusters. So the early formation time when these clusters basically viralize and so form the bulk of the halo in the inner region. Then you have a second time scale, which is basically associated with the dynamical time. So this is essentially the time it takes for material to fall into a halo, but it hasn't had time yet to viralize with the rest of the material. And then the third time scale is basically the time at which, on average, you had the last major merger inside the cluster. And so what this highlighted is that if we're trying to describe the mass profile of these clusters, we really need to take into account that there are two components to a halo. One is the relaxed, viralized one that happened at earlier times, and one is the dynamical, unrelaxed, infalling component made of things that are falling in and also major mergers that happen at recent times. And okay, this was good, but it still had a limitation, right? It still required basically humans to come up with these features of the data. So it still required me to say, okay, I want to test these particular features, which in my case were the mass accretion history, so the massive function of time. And it still required, to know that these features are relevant to predicting the final cluster. And so the goal really is to go beyond these models that require this featureization of the data and use convolutional neural networks and sort of bring them in the interpretable and explainable area of this diagram. Okay, so we did this in the context again of halo density profiles, but in this case, really focusing on the outskirts of the profile. So we know that basically within the halo boundary, or like the viral radius of these halos, we have, the profiles are dominated, as I said, by the orbiting material inside the halo. And we can more or less pretty well describe these profiles using some simple analytic function like the NFW profile and the NASO profile. But then when you start looking beyond the viral radius in this area where the profile becomes dominated by the infalling material, then the profiles we see in simulation strongly deviate from things like NFW or NASO. And if you look at the logarithmic slope of these profiles, basically you see this dip in the slope that is typically associated with the splashback radius of these halos, which is essentially the location of the first apocenter of material when it's falling into the halo. And this is, you can see it strongly deviates from the slope of the NFW, and the NASO model predicts that it's typically associated with the recent mass accretion rate of the halo. And we're interested in this regime because these features have cosmological signatures, again, related to the nature of dark matter or modified gravity, for example. Okay, so how did we do this? So we came up with this interpretable variational encoder. That's just what we called it. Could have called it something else, but I mean, which was actually inspired by a model that was done here in Zurich by Rabban Eisen from the computer science department. I don't probably know him, but it was inspired by people here in Zurich, where essentially, so the main feature of this network is this bottleneck that you have in the middle here. So the idea is that you start from your raw data. So in this case, it would be the density field in a cosmological simulation centered at the center of a dark matter halo. So this is a sort of a 3D gridded density field. And then you want to use that as input to a 3D convolutional neural network or an encoder that tries to compress all the information into a simple, low dimensional latent representation. And then basically this latent representation should, by construction, include all the information required to predict, in this case, the density as a function of radius. So there's a new input here to another neural network that again gives you the density as a function of radius, given this latent representation. So the idea is basically that this is this model compression. So compressing all the relevant information into this simple, low-dimensional latent representation that enables this explainability aspect of it. Okay, so what actually is this latent representation in a little bit more detail? So for those of you that know about machine learning, it's a bit like a variational autoencoder, but it's not unsupervised. So you're not, trying to reconstruct your input fully, but you're trying to only retain the information that is relevant to a given output. In this case, rho of R, so the density profile. So what does this latent space actually look like? So they're not just, numbers, but they're actually distributions. So what the encoder is really doing is that it's predicting the mean and the standard deviation of each of these Gaussian distributions for each of these latents. And then what you can do is that you can actually sample from this latent space to then give you realizations of what the density profile looks like. And so the key aspect for the interpretability part is that this latent space is disentangled. So what this means is that you have basically each latent encodes an independent factor of variation in your output. So you can think of the latent space basically like being the independent degrees of freedom in your final output, because each latent controls just one independent factor of variation in your final output. And so this idea of disentanglement is encouraged by the loss function. So the loss function that you're used to train and optimize your network is not just trained to give you density profiles that are accurate, but also it tries to trade off accuracy with a disentangled latent space. Okay, so this is just examples of the predictions of the density profiles given by this IVE, by this interpretable variation encoder, and you see, it's a band, okay, because again, you can sample the latent space and get a distribution for these density profiles, and you see, okay, it looks, pretty smooth, pretty fine, similar to an NFW, which of course we've cut at R200 to make it fair for the NFW model that was really only designed to describe the profiles up to that Vero radius. And you see that the IVE is able to extend beyond this in this regime that we're interested in for its cosmological signatures. Okay, so once you have this model, I've talked about the latent space being disentangled and being interpretable. So how do we actually interpret this latent representation? So what we use is a metric called mutual information. So this is actually a very standard metric used in information theory that is not so widely used in cosmology or in astrophysics at least. That basically allows you to quantify the statistical dependency between two quantities. So instead of just using something like a linear correlation coefficient that only tells you about the linear relationship between two quantities, you can actually compute the mutual information between them, which tells you both about the linear and nonlinear information between them. So what we did is that we computed the mutual information between each latent. Yeah.
Sorry, I sort of lost
yeah.
in the middle. Can we go back to the previous?
Yeah.
So you have this IVE model.
Yeah.
And then you train and then predict the density profile, and it matches the simulation just as good as the NFW is.
So the point was to model the profiles out to really the outskirts.
You mean the beyond the 200?
Beyond R200 to probe the splashback feature of the halos. And so we compare to NFW up until the R200, and you see that it gives you a pretty, smooth, well-fit profile up to R200.
Which NFW also does.
Yeah, exactly. So the point of the network is to predict the profile
And
up
it's
to 2 times R200, up to the splashback radius, where we have some analytic functions for, but they're
2 times that.
yeah, exactly. Out to 2 times R200 because that's enough to probe the splashback feature. Yeah. Okay, so what are these, latent parameters actually, encapsulating? So we compute the mutual information between each latent and the ground truth density profile of these halos. And so you see, okay, one latent has information about the profile in the inner region, and then basically no information about what's happening in the outskirts. Then you have another latent that basically has no information about the profile in the inner region, and then has lots of information about the profile in the outskirts. Then you can say, okay, I'm going to add a third latent to my latent space. And you see, okay, yeah, I have another third latent that has some information in these radial scales kind of close to the R200. And then when I add a fourth latent, this basically has no information about the profile at all. So what this, first of all, tells you is about the dimensionality of the problem, right? You need 3 latents to describe a density profile out to 2 times the Vera radius, and that's sort of the dimensionality of the problem. And it tells you which information, on which radial scales each of these latents have information about the profile. Okay, so then you can, play around with these latents and you say, okay, let me just fix 2 of them and vary one systematically and see what happens to the profile. So you see, okay, this latent that had information in the inner region, actually just moves the profile up and down. So it's really just capturing the normalization of your profile. And this latent B that instead has information in the outskirts is actually capturing the shape or the slope of the profile in the outer region, which is again sensitive to this splashback feature or splashback radius in these clusters. And then latent C actually is controlling sort of the inner slope of these dark matter halos. So then we thought, okay, can we actually try to exploit this latent representation beyond what we originally just trained it on? So when we trained it, we only gave it information about the 3D density field at redshift 0, so at present day. And we said, okay, from the sort of raw data from the 3D density field, give us the thing we're interested in cosmology, which is the density profile. But we know that, this density profiles of the structure of these halos comes from the nonlinear halo evolution through time. So do these latents actually retain information about the origin of the profiles, even if the machine learning model had never seen, right, how the halos evolved and how they formed in the simulation? So what we did was, again, compute the mutual information, right? The mutual information between the latent and this time the mass as a function of redshift, or the mass accretion rate, which is just the rate of change in mass as a function of time. And so what I'm showing you here is the mutual information between these 2 quantities for the outer shape latent and for the inner shape latent. And so you see, okay, the inner shape latent actually has information about the buildup of mass. So it's assembly history from early times up to a certain point, and then it doesn't really care what it does at later times. Whereas if you look at the outer shape latent, it's quite the opposite. So it really doesn't care about how the halo formed at early time. Was it through, I don't know, complex and major mergers, or was it through smooth accretion? It doesn't really care about it, how it formed. But then it has lots of information about the most recent mass accretion rate of the halo. And so what have we, really learned about these density profiles and about the origins? So on the one hand, I think, the IV actually recovers something that, was known 20 years ago. And this is the fact that the inner part of the halo, so what is typically quantified in terms of the NFW concentration, is correlated with the formation time. So this is, basically was shown in seminal work by Luisa Lucie, and then by many, many others after. And so the IBE just really rediscovered this known relation between the inner profile and the early assembly history. And then what it discovered, though, is really about this outer profile. So the fact that the outer profile depends on only one degree of freedom, only one parameter, that is sensitive to the most recent accretion rate, not to the accretion rate over many dynamical times or over a long period of time, but really the most recent mass accretion rate. And so, okay. Yeah, so what we're trying to do now is to actually apply this model to profiles that were measured from in the dark energy surveys by a weak lensing. You can measure these profiles of clusters, and we're trying to fit these models to these measured profiles in observational data and see whether we can actually constrain the mass accretion history of these clusters, because the parameters of these models have such a clear physical interpretation related to their assembly history. Can we actually fit these parameters to data and then constrain the mass accretion histories of the clusters in data?
Well,
Yeah. Yeah.
For this exercise up to this point,
Yeah.
you used, I believe, the dark matter simulation.
Yeah.
Dark matter only.
Mm-hmm.
And I guess that you fixed the halo finder and then the.
Mm-hmm. Yes. So this is also for this kind of like outer region, for the splashback radius, it's typically what is done also with analytic functions. You kind of tend to just find some empirical function from simulation of dark matter only because you're in a regime where you think that baryons don't really impact this splashback feature so much. But yes, in principle, one should then test it on different hydro simulations to see if the model can generalize to that. In terms of the halo finder, I think that's pretty robust for finding these clusters. So I think that's not so much of an issue. But of course, these are things that should in principle be tested against different halo finders and the inclusion.
But you are limited to massive halos, right?
Yeah, exactly, clusters, because it's where really the splashback feature is most prominent. Okay, so we've discussed about the density structure of these big parent halos, but we know that another key prediction of the lambda CDM model is what I was showing you at the beginning, all these tiny substructures that live within these dark matter halos. And so basically quantifying how many of these substructures we have and as a function of their mass, so the subhalo mass function is a really powerful probe also of the lambda CDM model. And so, how do we actually detect these small scale structures? And, one of the most interesting and most powerful ways to detect these small scale structures is via strong gravitational lensing. So essentially in strong gravitational lensing, you have a source and a lens here, and this is the typical arcs that you see when your source at the back is being strong gravitationally lensed by some source in the middle. And if you have subhalos in the line of sight of the photons coming from the source, you can detect them basically as an anomaly against an otherwise smooth lens. And so this is just an example of a strong lensing observation from Simona Vegetti in 2012, where these kinds of subhalos are really detected at the 10 sigma level, right? So you really need to have a subhalo there in order to provide a good fit to these kinds of strong lensing observations. And so what people typically do is that then they try to infer properties of those subhalos, such as their masses, and then compare them to the predictions we have from our cold dark matter models from simulations, for example. However, the inferred subhalo properties that you have from this kind of data very strongly depends on the assumed density profiles again. And so what we did is that this was work we did with Giulia Despali and Focus Pringle, is that we basically repeated the same analysis, but this time looking at substructures inside the halo. So your input now is not, the full density structure around the parent halo, but just some subvolume. It was done again in 3D. I'm just showing a projection here of a subhalo. And here, because we're looking at very small scales, we did do the analysis both on a simulation that only has gravity in it and a simulation that has the hydrodynamics in it. So both gravity only and the hydro illustrious TNG simulation. So we repeated the same analysis. We trained this model to predict this time the subhalo density profiles. And again, we looked at the mutual information between the latents and the density profile to see, okay, what latents did we find this time? And then we found, compared to earlier, quite a strong hierarchy in information between the three latents. So you have one that is basically actually dominating the variance of the profiles actually on nearly all scales. You have one here that is looking at what's happening towards the Vera radius. So in this case, we actually truncate. We only care about the profile up to the Vera radius because that's really all you need to estimate the subhalo properties that we care about. And then you have here another third latent, the subdominant one that, doesn't seem like it's carrying a lot of information, but it's actually quite crucial to give you the accurate predictions. And then again, when you add a fourth latent D, that is just noise. You don't need it to describe the halo. And what we find is that when we compare the gravity model and the hydro simulation, we see that at least qualitatively, we have a similar three latents. So what this means is that when you include baryonic effects, at least in the context of the galaxy formation model assumed by the illustrious TNG simulation, you don't really need any new degree of freedom to explain the baryonic effects. You just have small variations to the 3 degree of freedom that you would have anyway in the gravity model. Yeah.
So in this analysis, you train separately on the dark matter and the hydro?
Yes,
so,
there.
And because you know that the latent A is the same latent, could be just a very different combination of properties of the system or rate of it.
I'll show you in a second. Yeah, it would be a bit of a, conspiracy if they had exactly the same information as a function of radial scale, but they were completely different parameters, right? But it's a good question. I'll show you in a second. So again, you can look at, to gain more interpretation of what these latents are, you can again look at their effects on the density profile. So on the bottom panel, you see the hydro, and the top panel, you see the gravity. And so here you see again, the correspondence more or less matches between the latents discovered in the gravity-only model and in the hydro one. You have, again, just a normalization parameter, and then you have basically 2 shape parameters that are sensitive to the slope of the profile at 2 different pivot scales. So one of them is a pivot that is more towards the outskirts, and one is a pivot that controls more the inner slope again. And so what this parameter is really doing is that it's basically controlling when the profile tends to flatten towards the density of the background around that subhalo, and when instead it has a density profile that is still decoupled from the background at larger radii. Okay, so again, we didn't give it any information about what happened to the subhalos throughout its formation history, but we can try to interpret them by looking at the mutual information with the mass as a function of redshift, so the mass accretion history of these subhalos. And you see that basically this normalization latent has information about what's happening to the subhalo up until these subhalos then fall onto their current parent halo. So throughout their lifetime, they've been, basically like isolated halos, and then at some point at this redshift, they fall into their parent halo while they're orbiting. And so you see how basically 2 of the latents kind of decouple this information. One is sensitive to what's happening pre-infall time, and the other one is sensitive to what's happening post-infall time. And again, this is without knowing anything about when it's been falling or anything about its formation history. And then you see again that this inner shape latent is again, as we expect, sensitive to the formation history or the half mass formation time, the early formation time of the subhalo. And so what we're doing now is that we're essentially integrating this IDE model within the strong gravitational lensing pipeline. So just like you would do with with an analytic function, you can sample from this latent space and then fit subhalo density profile, this time basically predicted by the IBE decoder to the lenses that have been observed. And in particular, we are reanalyzing some lenses that have shown some very different concentration values when using, for example, the NFW model that, seem to claim that they could be different from what we expect from lambda CDM models. So we're trying to test whether, this was a modeling issue, or are they really not compatible from with what we expect from lambda CDM. How am I doing with time?
5 minutes.
Okay. Okay, so in the last 5 minutes, I want to talk to you a bit about an application instead to the halo mass function. This was the other kind of emergent universal property that I was talking about at the beginning, and this is work led by a PhD student that has actually now finished her PhD recently, Lilian Goa at UCL. Okay, so as I was saying earlier, we do have a theoretical framework which tells us that we can actually encapsulate all the cosmological parameter dependence and all the power spectrum information into a single quantity, which is this sigma, this mass variance of your fluctuations. And if you do so, you can vary, what is the number density of halos as a function of mass. You can rewrite that in terms of this f of sigma as a function of sigma, all on the same line. But then when, so this is basically what you would call a universal mass function, in the sense that it has a universal shape, the same shape for all these different cosmologies. But then when we look at this in simulation, we see that, this idea of universality really only holds up to 10%. And so it's insufficient for trying to extract cosmology from this kind of probe, from counting the number of clusters that we have as a function of their mass. And so what have people been doing to try to go beyond these universal halo mass function is basically relying on emulators. So essentially, as I was saying earlier, building these machine learning models that can predict halo mass functions that we observe in simulation, that we measure in simulation, so beyond just universal ones from the theoretical model, for many different cosmologies. And so you can have very fast predictions for the halo mass function as a function of redshift and as a function of mass. And so, of course, if you rely on these emulators, you lose, any theoretical understanding of what could be the origin of non-universality. And, the slight limiting factor of emulators is that they're always really limited to the domain of validity that you trained it on. So as we want to explore more cosmological parameter spaces, we always need to retrain for the new set of cosmologies. As we want to explore, higher dimensional cosmological parameter space, you end up having to sample this very large, high dimensional parameter space in order to faithfully and robustly train these emulators. So what we wanted to see is, okay, well, what drives this non-universality, and can learning about this actually inform us of more efficient training set designs? And so again, we applied the IDE to this problem. So the input this time is just the power spectrum, or the power spectrum and the growth function of a given cosmology. Here, the encoder is much simpler, right? It's just a 1D artificial neural network, fully collected neural networks. You don't need any more the 3D CNN that I heard earlier, because your input is in 1D. And then you want to encode all the information in this linear representation that gives you n as a function of n, so the halo mass function. And so questions were, how many parameters do I need to describe this halo mass function, and can we isolate and quantify the universal and non-universal information in this quantity? Okay, so the first thing we found is that, okay, again, 3 latent parameters are required to describe this halo mass function. You can see here basically the accuracy of the IDE of the model when trained on a 7-dimensional latent space, which is actually the maximum you could have, because our cosmological parameter space is 7 dimensions. So that's kind of the maximum number of latents you could ever have. a three-dimensional space, a latent space, and a 2D one. So once you have a 2D latent space, you see your error bars blow up, meaning that you need more latents, you need more information to be able to give you a good prediction for the Halo mass function. And the second thing we found is that, a lot of the literature has been focusing on claiming that the growth function is what is responsible for non-universality. But what we found actually is that with the machine learning model, we found no improvement if we add growth function as input to the model. And so we can actually reproduce the Halo mass function at the same accuracy given just information about the power spectrum alone. Okay, so once we have again these three latents, we can look at what they're capturing, and we find again quite a strong hierarchy between these latents. You really have two dominant latents. One of them is measuring basically the abundance of dark matter halos on high mass in the high mass regime, and one of them is measuring more of a slope and the abundance of halos at the low mass end. So these are really the two most dominant latents. And then you have a third very subdominant one that is actually, I will show you in a second, capturing the non-universality component of the Halo mass function, and is given sort of this correction to the slope of the Halo mass function. Okay, so we find that, the universal latent, so the latent that is controlling the abundance of halo at the very high mass end, is sensitive to SA. This is again something that's quite known in the literature, that the high mass end halo mass function is sensitive to this parameter S8 very, very well. You see there's a very tight correlation between the two, except for some tiny scatter with respect to omega m. While the second latent is actually capturing this mapping that I was telling you about between N of M and F of sigma. So it's turning the N of M prediction into the universal F of sigma. And so this is again the correlation between the latent and this quantity with some residual residual scatter that is sensitive to an effective. The non-universal information of the Halo mass function, on the other hand, is captured a little bit by again this mapping latent, and in particular its cosmological dependence with omega m, but mostly with the non-universal latent. So this third subdominant latent that turns out to be essentially well described by the late time growth, so the growth at late times, and an effective. So what we're plotting here is actually a conditional mutual information. So the mutual information between two quantity given knowledge about something else. And what we find is that, the non-universal latent basically has no more information about F if you know about DZ late and N effective. So this means that the late time growth and N effective completely capture all the information there is in the final non-universal latent. And so what we're working on now is actually trying to, instead of constructing emulators, starting from sampling the full cosmological parameter space, we can actually construct them by sampling in the direction of these latents. So instead of constructing new emulators for each cosmological parameter space, you can just sample in the universal and non-universal directions to give you emulators that are generalizable to other cosmologies as well. Okay, so let me just conclude here by saying that, we wanted to achieve this idea of interpretability and explainability via a combination of model compression and then the metric of mutual information. And in particular, what the IVE does is that it essentially disentangles the different physical effects into a minimal set of independent ingredients. And, we started working on these emergent logical structure properties, density profiles, accretion histories, and the Halo mass function. And yeah, we hope to apply them to many more things in the future. Thanks a lot for listening.
So I'm very interested in your subhalo mass function
Mhm.
analysis together with Julia.
Mhm.
Can you go back
Yeah.
to what, when you explain what you're going to do?
This.
Yeah. So if I understood right, like, so you want to compare what like Simona found with her concentration parameters that didn't match lambda CDM.
Yeah.
And so I'm wondering whether this is in a sense like a fair comparison, because like the statistical analysis of what she does is like in a sense like a bit different than what you are going to do. Because like she used like the Bayesian inference.
No, so this is going to be integrated in that same inference, but
Oh,
instead of fitting the NFW,
yeah.
you fit this, but it's the same, right?
So the way of then like getting the conclusion is the same.
Is the
but you
same,
just
but
like
I'm
get,
just
like,
changing the
function
model.
to
Yeah.
Okay.
I'm just changing the model, and the idea is, again, because you have, I mean, in this case, like a good prediction of the model, right? Oh, a good prediction of the profile, because the NFW actually just doesn't predict very well the subhalo density profile. And then you have very small number of parameters, which was the other important thing. Otherwise, you're completely unconstrained. And the parameters that actually mean something physically, right? So in principle, you can even set very tight informative priors, because you know very well that one of them depends on the early accretion phase, and that you can set good priors, and maybe not so well on the late times in falling part, but you see what I mean? You can inform it instead of having a very broad mass concentration relation that, So we're hoping that these improvements make it a more fair test of lambda CDM, and
Really good. I'm looking forward.
Yeah, sorry, maybe I didn't quite understand the very last part. So you have latents and you make correlations against parameters that you know.
Yeah.
So an effective is something you've chosen.
Yes.
That hasn't come out of the system in any way. And the late time growth hasn't either. You've chosen that and made the correlation plot with that parameter and your late time.
Mhm.
And now you're saying you can do the inverse, that you can create a model by varying, say, an effective or the late time growth and produce a viable model. This, I think, is not clear to me that we can do that.
Yeah. So, I mean, the way we're doing it is that we're basically creating a mapping between the two. So in other words, imagine that you don't start from the cosmologies, you start from late time growth, and then you vary that, and that has a correspondence in parameter space that isn't just related to one cosmology, but multiple, because they're degenerate.
Yeah, the
And-
motivation is clear.
Yeah. So what is unclear then?
So what's not clear to me is that actually works. I mean, that you haven't missed some parameter that you haven't. You've chosen an
Yes,
effective and key growth, and they correlate with one of the latents, which we want to understand, or both of them correlate with one of the latents. You know, to me, it's not clear that you can then train a model by choosing that particular thing that hasn't fallen out of this procedure in any way.
Yeah.
You just chose it after the fact. Say, oh, it varies with this parameter.
Yeah. No, I agree. It's not obvious that it can improve emulator training sets. That's not obvious, and that's what we're testing. But what we're saying is that, now you're sampling 3 parameters, 3 latents, when in principle, I mean, we already know that it can cover 8 to 9 dimensional parameter spaces. So that's already a huge improvement if you can sample, even if it doesn't actually generalize to more cosmologies than the original ones. Already the fact that you just have to sample in 3 directions already gives you a large improvement in the training procedure. But on top of that, given all that's the hypothesis of the project. I don't already know the answer, but yes, the hypothesis is that given that this direction is correlated with many parameter space regions of different cosmology, then we could do that. But we're testing that. I agree, it's not obvious that it will work. It's also a question of to which accuracy, right? this is a super accurate model, and maybe you can get away with less accuracy for cosmologies that you're extrapolating a bit on. So it's also a matter of the accuracy with respect to a standard emulator, for example. Yeah, I agree. There.
Well, maybe I'm have a very naive view of this, but this learning of these legends, this reminds me of principal component separation. Is there a relation?
Yes,
like
I mean,
just rediscovering the principal component?
yeah, you can think of it like PCA, but non-linear. That's the crucial aspect of this, right? That PCA will always give you a linear decomposition, whereas you can think of basically this convolution neural network giving you non-linear PCAs. That's exactly the right way of thinking about it. Like a non-linear PCA. Yeah. Yeah.
I have a more general question. So one of the criticisms that's sometimes leveraged against AI, especially so explainable AI, that we haven't really made any really new discovery this way, right? So most of the stuff that we find this way, stuff that are kind of known, 95% known, and maybe they'll look, adds a little bit more to it, but it's not kind of ground shaking. So first of all, so my question to you is, do you agree with this kind of criticism so far? And also, what can we do in order to, kind of improve it and really kind of learn more about it?
I mean, I don't know. I don't think I need to comment particularly on criticism. I feel like a lot of the time people expect AI to discover new physics out of nowhere. I mean, I think it's typically criticism that comes from people that haven't actually worked with AI. I mean, I think one shouldn't expect of a statistical tool to do anything different than other statistical tools do, which is, telling you something about the thing you've trained it on. So I don't see why it's a criticism to explainable AI. I think it's probably because we have not, I mean, I don't know of many works on explainable AI that go beyond, for example, visualization techniques like saliency maps, or, this was really one of the first applications that we did. And I think it has discovered things about the outer profiles, and that can then inform us on how to build models that we've been trying to build for 20 years, right? Trying to model something like the splashback radius. So it depends, if you're trying to get AI to give you a new physics and a new theory of gravity, I mean, no, it hasn't done that. Has it learned something new in the context of what you applied your tool on? I think it has. I also think that these models have to be very strongly validated, and applying it in very nonlinear regimes where you have baryonic physics becomes difficult, not because of the AI could totally do it, because we don't have reliable training sets. We don't know how to train it given the uncertainties that we have in simulation. So I think sometimes, I don't know, it gets blamed on ML, and it's not actually ML. It's we don't have simulations, we don't have training data. And so, yeah, I don't see it as a criticism of the tool. I see it as a criticism on the applications that we've made out of the tool. But yeah, I think there's tremendous progress being made in the last years, and hopeful.
Well, about the word explanation here in this context.
Yeah.
What is the difference between, because I can argue that if I just build an emulator, I also have a sort of explanation, but the explanation here would be FO equals MA, because it's all that I actually doing physically to do cosmology, right? I don't know the explanation on another emergent level, let's say, that what you are trying to do, I think. So basically you are trying to say, no, instead of this brute force approach of emulators, I will learn the transformation between this latent space to this observables, and then I can try to interpret these latent variables in terms of the cosmological parameters, for instance. That
Yeah.
fair?
I mean, so explanations obviously are tied to your sign question, right? So there's no such thing as explainability in isolation. It's explainability tied to the science domain and the science question that you're asking specifically. So I can tell you in this case, you know, for example, in structure formation, right? There's been people are running simulation and doing that. And on the other hand, people are building analytic models, right? So for example, to try to infer from the initial conditions, what is the origin of the spin of dark matter halos, or what is, you know, the origin of assembly bias and these kind of questions. And they've gone hand to hand, right? So you, on the one hand, you have a brute force ways of doing, I would say, the microphysical theory, so just gravity, and on the other hand, trying to understand the macrophysical physics. So what is the origin of structures in a way we can understand it from a macrophysical sense. So to me, what at least the way I've been thinking about this is more on the macrophysical side, right? Doing what analytic models have been trying to do, trying to predict, again, like tidal torque theory, excursion set theory, like these kind of models, going beyond the limitations of the analytic part. So enabling you to model the nonlinearities with a more flexible machine learning model, but trying to still understand that theoretical question that you have. And then, of course, it can then be applied to things like also excursion set theories are and so on. But that's the way I define explanation in this context. But of course, it can mean different things in different contexts. It's definitely not an absolute definition.
And about the excursion set, excursion set is able to give an explanation as well for the F of sigma, right?
Yeah.
There is a prediction for that.
Yeah.
So I haven't mentioned, but I remember correctly.
Yeah, so the work we did with the Halo mass function was really trying to go beyond that, right? Beyond just F of sigma and explaining the scatter in F of sigma as a function of sigma, which is what excursion set can't explain. Right? So excursion set gives you a universal mass function. And we were trying to explain the scatter in that universality prediction, which is what we need for classical cosmology. But I did a lot of earlier work actually comparing apples to apples the excursion set and the machine learning models to try to test some of those hypotheses related to the impact of tidal shear in the initial conditions. And so we can chat about that later. It's something I'm still super interested in. Yeah.
So let's thank again. People that are going for lunch, we are meeting